Okay, we have SDSSN. So this is our website, sdssn.org. So once you have it, you click on it, it opens, and then you have this interface. If you're not logged in, why it is like this? Because I've logged in, but okay, let me log out now and then log back in. So we start afresh. So this is the interface. Once you click on the website and join us, you put in your details and then you log in. So this is your dashboard, your profile. So this is my own profile. And for you to get your certificates, so there are actually two ways to go about it. This is our landing page. You can do that from here, membership. So these are our 4 categories, like I mentioned earlier, and these are the amounts each category is going for. And trust me, each category has its requirements as well as amazing benefits attached to it. So these are some of the requirements, and then these are some of the benefits that is attached to some of these categories. So if you have you're on this page, the other way to actually go get your certificate is certificate request. So you see that we are still in the same page. So depend on the one you want to go for. I've applied for one, so let me use another one. So I'll be applying for the associate member. So this is the fee attached to it. You tell us the reason you're joining, you upload your credentials, and for the associates, these are the credentials required. You have your professional ID card, you have your CV, you have your 2 recommendation letters, and at least published articles on the website. I understand that when I logged in, you saw an article that was published. So those are the kind of articles we are talking about. So those are the kind of articles we are talking about. So every category has its own requirements. And then once you have applied, we will get a mail, and then your your documents will be reviewed, and it will be approved. When it's approved, you will get a mail confirming the approval of it. So after that phase, this is another phase for you to, sorry. So this is where you get to check your certificate status, if you've paid, if you've not paid. And once you have paid, you get to see this, my membership. And this is my certificate. And this is a UR code for you to verify. And trust me, it is one you wouldn't want to miss out on. So thank you everyone for sticking with me up until this moment, and I would stop sharing now and then welcome our facilitator for the day. Thank you.
Thank you very much, Bridget.
So our facilitator is in the person of Ajiyomi Samuel, and I'm sure we all are itching to know what the session today is all about. And trust me, it's going to be an amazing time. Stick with us and enjoy the training. Thank you. Over to you, Samuel.
All right, thank you. Can you hear me?
Yes, I can. Go ahead.
All right,
if you can
thank you
hear
very
us, please, you can just indicate with an emoji. And if in the course of the training you have questions, sorry, Samuel, I'll hand over to you in a bit. If you have questions, you can just leave them on the chat box, and we will attend to them. And please endeavor to mute your mic so that you can have a quiet and smooth session. Thank you.
All right, thank you very much, Rekia. Thank you for the introduction. Good evening, everyone. My name is Ajomi Adedoyin Samuel. I am a geospatial specialist, and I have experience in working both as a geospatial analyst and as a geospatial data scientist, as well as currently I work as a geospatial data engineering. I have been opportune to actually I've also had experience of working as a geospatial backend developer. So I've been opportune to actually work around different different niche of GIS, and across the year I have picked up 1 or 2, 3 skills from being taking up these roles. So yeah, it's good to have everyone here. And also special thanks to SDSSN for organizing something like this. And according to what Ricky has said, SDSN is actually a platform that is actually letting people to know that there's more to GIS than just creating point map, polygon, or choropleth map. There's a lot that you need to actually uncover. So today's session is going to actually have two parts. The first part is I'll be talking about some things, and then the second part is where we'll be doing the hands-on. I don't plan to take much of our time because I understand that these days people tend to have um low attention span. So, and people want to get as much as they can get in as little time as they can. So I will try as possible to make justice to what I'm here to teach us today. And as well as, do the practical so that we can all experience some things that we haven't. So thank you. I'll be sharing my screen now. All right. So if you can see my slide, can you please just um, let me know by maybe sending an
Yes, we can
emoji.
see.
All right, all right. Thank you very much. So yeah, I'm going to start now. Please and please, this is very important because I will tell you something. While I was trying to like learn a lot of all these things at the beginning, that was around 2020, 2019, I kind of like have issues being able to like understand the differences between a lot of things, being able to understand their importance where I need them, because that's the issue with being a GIS analyst. There are a lot of tools that is actually available that can be useful for what you are doing. But because you don't know that there are other ways you can do these things, you tend to stay on the same way in trying to do them. So why I will try to explain, I would love us to pay attention to everything I'm going to be saying. Thank you. So I'll be speaking on the topic spatial statistics versus geostatistics. Well, there's no versus there in the real sense of things because they all serve different means when it comes to geospatial analysis. So, but we need to know the differences so that we need to know where to apply spatial statistics and where to apply geostatistics. So my introduction part is to do general introduction to like spatial analysis. So spatial analysis, when you talk about spatial analysis, is a broad field that uses location data to answer questions. So we try to, to review pattern and support decision making using geospatial data. So when you are talking about spatial analysis, there are different ways you can do spatial analysis. And I don't know if I exhausted the list here, but these are some of the common method or common means people tend to do their spatial analysis. Number one, spatial statistics. Spatial statistics is actually used to help us to understand spatial pattern and relationship. Like you collect points, you want to understand the pattern of those points. Let's say you have crime data now. You want to know if this crime event are clustered or dispersed. If you want to do this thing, you need to employ spatial statistics. So when you are actually trying to know, oh, is it clustered? Does it happen randomly? Is it dispersed? You need something like spatial statistics. When you're trying to understand the relationship between that crime and let's say population, you understand, you need spatial statistics because you need something like ordinary least square, you need something like geographical weighted regression to be able to understand the relationship between the number of crime in a particular location and the population or different tribes, because in some tribes they know, oh, wherever some tribes are staying, there tends to be more crime in that area. So now you need to understand the pattern at which people live at that particular area for you to be able to like, compare that. And sometimes it might be unemployment. So you can have the map of Nigeria and you have the tribe data in the whole state of Nigeria, and then you now have the unemployment rate in the whole state of Nigeria. So you can use spatial statistics to understand that, okay, is this location based? Does it have anything to do with location or it is just happen randomly? So when you perform spatial statistics, you can then decide what to do. That's what spatial statistics is all about. So there are a lot of algorithms there are a lot of model within spatial statistics as a whole. We have the Mora-I, we have the OLS, we have the GWR, we have a lot of them, and we'll be looking at some of them today. And then when we go to the geostatistics talks about when you want to model continuous data or phenomenon, like you want to predict something that does not happen in a location. For example, you go to the field, you collect soil sample. Now, when you are collecting that soil sample, you then collect for every inch of soil in that area. You only select a particular location in that area. You can do random sampling. You can do a stratified sampling whereby you divided the place into maybe 10 or 20. And then you take soil sample from here. After you take those soil sample, you actually take them to the lab, and then you get some chemical variables or chemical quantities of those soil. Then now you add this data back to the point, and you want to now know the distribution according to that area, or let's say that farm. You need to do something like geostatistics to like have the prediction. I know generally people use IDW, yeah, inverse distance weighted IDW. People use that very well. But IDW is one of geostatistical too. Is not the only one. You know, we have Kriging, we have empirical BBK, we have a whole lot of them. So when you're trying to predict continuous variable like your rainfall, air pollution, PM2.5 across a particular area, and you want to have a statistical support around this thing, that is when you use geostatistics. Then let's talk about GeoAI. GeoAI has been the buzzword that is going on. So what is GeoAI? GeoAI simply means adding AI and machine learning model to solve GIS problem. Like you want to do your classification, you want to do your prediction, you want to do image segmentation, you want to do object detection on satellite imagery, you want to do similarity search. So application of machine learning and AI into geospatial data, satellite imagery. That is what GeoAI means, which means if you want to learn GeoAI, you first need to go and learn machine learning. You need to go and learn deep learning. You need to know how all this model works. Then you now taking all these things you've learned from data science and applying it into GIS. It was GeoAI mean. Then we have raster and imagery analysis, just like your NDVI. When you use your raster calculator, you do something like change detection, you do something like even some classification model are not AI and ML. Some maximum likelihood is just a statistical classification model for your raster analysis. You know, you want to do your suitability analysis using AHP or weighted overlay, all those things, they are raster and images analysis. Then we talk about networking and routing. So this part of this are actually all these things you see on my screen are a niche on their own. Honestly, they are a niche on their own. But if you are very good and you are someone that has used GIS a lot, you can learn all these things, but they are a niche on their own. When you're talking about network and routing analysis, you are mostly talking about the mobility sector because you want to understand the distance, how people are moving, you want to calculate the shortest path, you want to do you want to understand traffic and how it influences people. You want to build a model that helps to identify the best place people to go. You want to do accessibility analysis, logistic modeling. Network and routing analysis is what you do. Then we also have the 3D and spatial temporal part. 3D and spatial temporal part, your 3D can be your SYZ, which is longitude, latitude, and location, and it can be SYT, which is longitude, latitude, and time. So you can do all this analysis. There are areas where these are very useful. And then when we talk about vector-based spatial analysis, these are when you try to do your buffer, you try to do your clipping, you try to do your merge, erase, you try to do your intercept and everything. So everything we are doing at this point has to do with geometry analytic. So that's what vector-based spatial analysis mean. But for the sake of this class, we'll majorly be picking the first two, which is spatial statistics and geostatistics. And why are we picking these two? Because we realize that a lot of people do not really know the difference between these two. A lot of people do not know how powerful these two are. A lot of people do not even know different method under these two. So we'll be talking about it. So I'll be talking about spatial statistics first before I go to the second one. Yeah, I'll be talking about that. So what is spatial statistics? So this is an analysis method that use location of feature. So location of features to detect pattern, cluster, relationship, and spatial processes. Keyword, you use analysis method to detect pattern. Like I said, you look at crime, you look at clash, you look at diseases that are spreading. You want to understand the pattern that, okay, is this thing cluster? Is it spread? Is it happen randomly? So you don't just plot. That's the thing. You are a scientist. A lot of time, people just plot this point and they'll be like, oh, towards the southern part of the data, I can see that it is cluster. That's not how you do things as a geospatial scientist. You need to use geospatial tool to prove that at that point they are cluster. So you need things like get all these tool, hotspot tool to be able to understand that, okay, really, these things are really cluster. It's not just you using your eyes, because when you run this analysis, they return the Z value, the P value based on location. And this thing can actually now be used to support your motion. So it's not just you taking things away from your head, because you are a scientist, you prove things by facts, by values. You don't just say it out of your mouth. So these are very important. So you use this method when you want to analyze things like crime incidents, disease cases, road accident, schools, like you want to understand, are there too much schools in this place? Where are the location where we don't have much hospital? For example, maybe there is a disease and you want to actually know the cluster of the disease. You can now run a spatial statistical tool to know the hotspot, and you can now overlay your hospital location on it to know, okay, oh, these places where we have crazy hotspot of these cases happening, we only have few hospitals. So these are the way you actually integrate your spatial data together. So key focus of spatial statistics is to detect pattern, hotspot identification. You want to understand spatial relationship and spatial autocorrelation. So some common method that we use when we are working with spatial statistics: number one, hotspot analysis, that get this or this. I know sometimes some people will say they want to do hotspot, they will go and be doing point density. Point density is not really hotspot analysis because there's no statistical result behind what you just run. You are not getting the confidence interval of the place being hot or cold. You can only get that from your hotspot tool is spatial statistics. So if you go and run your point density without all these metrics, you are just trying to just know you are just trying to weigh your point. That's just what I can say about that. And then when you talk about spatial autocorrelation, like moral eye, you want to know if things are, just like the way you have hypothesis, we don't just spatial hypothesis. We call it CR, is it CRS or so, or CR? We call it common randomness something. I've forgotten that now. So your first hypothesis as a GIS person is that you to ascertain that everything is random. You are not supposed to, so you cannot have an H1, which is your null hypothesis, to reject your null hypothesis that, okay, these cases are not random. So when you run things like moral I, either the global or the local, you can be able to know if you should actually accept the general randomness hypothesis of GIS, or you've seen something that is not random. So some tool you can use to run this are, you can use your cluster analysis, cluster outlier, Anthony Looker. Anthony Looker is one of my favorite tools, because what does this does? This actually help you to actually know outlier within hotspot. So that when you run your hotspot analysis, because some places are close to each other, it can use the distance between those features to say they are hotspot. But when you run things like Asselin Local, it helps you to it helps you to understand that, okay, even though I recognize this place as an hotspot, but I only recognize it as an hotspot because it's within hotspot. It's an outlier based on this event that is happening. So what question does spatial statistics answer? It answered question like, are this feature cluster or dispersed? So when you want to ask this kind of question, use spatial statistics. Which area are statistically significant? When you're talking about hotspot, use spatial statistics. How does distance influence interaction? Now you are talking about two variables. You want to understand. For example, there is this global Facebook data that was releases during COVID-19. You can take that kind of data and you can take some distances data to understand human movement that was created by Facebook. You can put this data together and run the spatial statistics to understand that, oh, is distances influencing interaction, or people does not move more, they interact more. So that can be a research topic for anybody to actually understand. So you can also understand, does location explain variability in a variable? This is very important. Just like I said, you have crime data. You need to understand, is this crime happening as a result of the location? Because it can be random. So you need to understand. So when you are trying to answer this kind of question, you use spatial statistics. So use case of spatial statistics include crime hotspot mapping, disease clusters detection, urban growth pattern analysis, flood incident clustering. Like you can have different points of flooding over the years, and you can just try to understand that, oh, where do we have high cluster of flooding occurring? Where do we have low cluster? So you can do that. Then you have pattern of reported cholera cases, like you have cholera cases, just like the way we have COVID-19 in the other time that you want to understand, or you want to understand the distribution of school or health facilities. So you need something like spatial statistics to run all that. I have a story. I think I will just say the story. So I remember my days in the university. We were doing a presentation, and someone do analysis on distribution of bus stops just to help the driver. And so in the person write-up, the person started telling you, when you look at the northern part, you will see cluster. When you look at the lower part, you will see cluster. So when the person was doing the presentation, the professor stopped him and said, "We are scientists. What are the analysis you run for you to be able to say you see cluster here, you see the cluster here?" The person said, based on the map, that the person can see it. But the person was stopped from presenting. Why? Because there are some analysis you can run that will give you some, you have some p-value. For example, now, if you run Mura I, your p-value should be, your p-value and your z-value, they should be less than 0.05. Then you can generally accept that there is a cluster effect happening there. So all those things are some of the things we are going to look at. So let's talk about geostatistics itself. So what is geostatistics? I've talked about spatial statistics. Now I'm talking about geostatistics now. So it is an advanced spatial prediction. This has to do with prediction techniques based on spatial continuity. When we mean spatial continuity, it means the variable is a continuous variable. So it is mostly used for interpolating surfaces. Just like I said, you have some sensor that collect PM2.5, that collect air quality, that collect a lot of data. So those sensors, they only collect for a particular location or within a particular distance. Now you need to create a surface that will show this thing for the whole state, or for the whole farm, or for the whole area. You need those statistics to do it. I think everybody uses IDW. Yeah. But if you are really a scientist, you have to go beyond the IDW, because there are a lot of, the IDW is part of the tool, but there are a lot of things you can do inside geostatistics. So geostatistics is designed to work with continuous spatial variable. I hope I'm not too fast. I hope I'm not too fast. Okay. So geostatistics is
Somehow,
designed to
just
work.
slow down a bit.
Okay. All right.
A bit.
Geostatistics is
Thank
designed to work with continuous spatial variable where value gradually changes across space. Just like I said, you collect different points at different location, and you want to actually build an interface map to show for that area. So you need your statistics to actually interpolate for those places. So it's like, let me give you an example. It's like you go to 10 local government to collect some sample, and you have 18, and you want to create a soil map that cover the whole 18 local government. So you need those statistics to actually predict for the remaining 8 local government, so that you can have a balanced surface, so that at the end of the day, you have a balanced map. So key focus of these geostatistics, including when you are trying to quantify spatial variability. Spatial variability means spatial changes. You are trying to understand the changes of, let's say, rainfall or any of this pattern. You are trying to model similarity decrease with distance, because this has to do with distance, the point where this stuff are collected. It can even be a rainfall. You understand? You can collect rainfall data for different locations, and you want to use it to create a bigger map for Nigeria or something. You need your statistics. Predicting value at on sample location. Just like I said, you sample different location, but you need to also know the value of sample location. So you need your statistics to do that. So you also need it to measure or certainty or prediction. And this is the thing about your statistics. It doesn't just predict those locations, it also show you the error. And you know, those people that are into machine learning, they will understand that you need to actually compute all this, your RMSE, you need to compute your accuracy, you need to compute your R square for you to be able to ascertain how your model is working well. These are some of the things that geostatistics actually has. So some of the method that is used in geostatistics are, you have ordinary kriging, universal kriging, empirical Bayesian kriging, you have your variogram modeling, you have your surface interpolation and IDW. We'll be looking at some of these things as we go on. So what question does geostatistics actually answer? So it answers questions like, how can we estimate value at a sample location? I've already said that you collect for different locations, you didn't collect for some location. You want to predict for those locations you didn't collect from. Go and geostatistics. What is the spatial autocorrelation structure? Geostatistics also accepts some variable as dependent variable. So we are going to see all that. So you need it. What are the significant hotspot and cold spot in my data set? So when you do your prediction finish, you can easily see that. What is the level of uncertainty in my spatial prediction? So after you do your, when you do your IDW, you don't get error, you don't get statistics, you don't get model, you don't get anything. You just get one result, bam, you put it. But in just statistical two part, you get to see all the error of your prediction, your error of your sampling, you get to see different formulas, different representatives, so that you can actually go and present this and tell them on how good your model is performing. So you also help you to optimize sampling. Yes. So maybe you go and you can actually go to a farm now and collect this geostatistics is actually used by people that do soil sampling a lot. So let's say you go to a farm of 5 hectares, you decide to divide the 5 hectare farm into like 50, and then you take each box of 50, you take a sampling, and then you take it to the lab, and then you now use it to estimate for that particular area. You can now use like 4 or 5 to validate what you estimate. If you realize that your prediction is not predicting well based on comparing those 5 with what was predicted, you can go back again and maybe increase your sampling to like 100. So that way you will get a better result. And when you are now advising the farmer on what to plant and how to plant, that data will be more useful. So use case, you have soil property estimation. We are going to use that. Rainfall mapping. So like in Nigeria now, I don't know how many sensors we have even in Nigeria. Imagine you have the sensor of all, you have the rainfall data from every sensor in Nigeria, and you want to create rainfall map for Nigeria. You need your statistics. Air pollution modeling, PM 2.5, NO2. You need your geostatistics. When you talk about underground resource estimation, for the geologist or for the geophysicist, so they can go to a place and then they take some sampling from underground and then they bring all those data to you. You will need to create a underground map that will actually show the below the ground in 3D. You need geospatial statistics. For groundwater depth, groundwater quality, soil organic carbon, you need geospatial geostatistics because it has to do with surface modeling. So anything surface or beneath the surface, you need it for it. So I did this comparison. It's just a small table, and there's a reason why I put GeoAI here. I understand that the buzzword in the geospatial domain has been GeoAI. All of us want to GeoAI, but it makes sense when we understand what we are trying to do before we jump into them. So this table is just to help you to understand where you need spatial statistics, where you need geostatistics, and where you need GeoAI. So let's say your primary goal is to understand spatial pattern. So that's the primary goal of spatial statistics, understand. That does not mean it cannot do more than understanding spatial pattern. It can do more. You can even use spatial statistical tool like MGWR, like GWR. We have a regression model that you can use to predict continuous variable. But that's not the main goal of spatial statistics. Even when you run all this analysis, you see that they help you to understand this data. Okay, let me just say this. One of the advantages of spatial statistics over the normal data science we do when it comes to regression is that your normal data science, we give you an overall R-square value, we give you an overall error value, we give you an overall accuracy value. But what spatial statistics does is that every point, if you have 12,000 points, each point have their own accuracy, their own R-square, their own expected, their own error. Each point have it. That's one advantage of it over the normal traditional. Maybe when you are using random forest regressor, or you are using linear regressor, or you are using supporting vector regressor, any of the regressor, even if it's gradient boosting, at the end of the day, when you are trying to calculate your R square, your RMSE, they give you only a single value. But in GIS, every boundary, every point give you that error score. So geostatistical is actually used to predict missing value. That's the primary goal. It can do more than that, but that's the primary goal. Why GeoAI? It helps you to actually learn pattern. You know what ML mean. Like I said, you need to go and learn ML and deep learning and then apply to GIS. So it helps you to learn pattern and automate prediction. So the data type you need for the spatial statistics is point, polygon, and network, like line. You don't need raster for it. For the geostatistics, it is continuous feed. Continuous feed can be a raster, it can be a vector. Before, the geostatistics go to in ArcGIS Pro does not accept raster, but right now they now accept raster. So it can be a raster, it can be anything you want. Then for the GeoAI, we talk about big data. You talk about imagery, you talk about vector, it takes its own name. So they are theory based. So what their theory is all about. So when you're talking about GeoAI, all the theory of GeoAI is machine learning and deep learning. So if you're interested in GeoAI, go and learn machine learning and deep learning. Then for geostatistics, is all about spatial continuity, continuous data. Then when you talk about spatial statistics, it's all about spatial relationship. Then some tool in ArcGIS that you can use in this. ArcGIS actually have a deep learning and a machine learning toolboxes. So you can do GeoAI inside ArcGIS Pro. And then for the geostatistics, you have your grading, you have your variogram. We are going to check all those things out. And for your spatial statistics, you have your hotspot and your moral eye. Those are part of it. So the output of your spatial statistics tool include clusters. You see a map that show you cluster, you see a map that show you pattern, and you also see statistics that actually validate this pattern. And for the geostatistics, you have a surface or a raster data that show you a continuous variable. And then for the GeoAI, you actually have a classification or prediction result. So what are they best for? Spatial statistics for pattern discovery. You want to understand pattern. Geostatistics is for environmental surfaces. I think it's in the environmental field that we do most of all this surface prediction, like air quality and the rest. Yeah. And then for GeoAI, for intelligence automation. So I think I'll just go through this very fast. Application area of geostatistics, of spatial statistics. So you can see that it works best for pattern analysis, not prediction. Like I said, it can do prediction, but it works best for pattern analysis. So you can see in public health, you can use it to like identify malaria and cholera clustering. You can use it to track disease diffusion across world. For the urban planning, you can use it to identify underserved zone. And for that underserved zone, imagine you went to actually distribute mosquito net in a particular place and you collect points of those mosquito net. You can now collect those points at the end of the day and run a hotspot analysis. And you will see where they have you can see where they have more nets than the other. You can now overlay this on the satellite imagery or a building shape file. You can now see that these places that you went to distribute low number of net. There are many building there. What's going on? So that way you are able to understand another serve zone. So you understand distribution of social amenities. Crime, when it comes to crime analysis, use it for hotspot detection. You understand risk and concentration pattern. For transportation, accident, for environmental management, you can map illegal job site monitoring, clustering. You can also use it to study deforestation pattern cluster. And for people in the demography and social science, they can do spatial inequality analysis. We used to do that a lot. For population density mapping. Yeah. So some ArcGIS Pro tool that you can use for this thing, you have kernel density estimation, you have spatial autocorrelation, you have GWR, Mora-High, and etc. We'll be going to them one by one. And for the geostatistics, as you can see, agriculture, very important, hydrology, climate and weather, air pollution, natural resources. So these are areas that you need geostatistics for. So I'm going to give out this slide. I think we'll be sending them out after this class when we probably send the recording to our mail. So yeah, we don't need to dwell too much on this. Let me just summarize everything we've talked about. So we've talked about spatial statistics, that you need point, line, and polygon to do it. You need it when you want to understand pattern, cluster, or relationship. The variable are mostly categorical or numeric. So the question is asked is, why is this happening here? Like, you want to know. So that's it. And for the geostatistics, your data must be continuous. You need it for prediction for area that are not sampled, like area they did not collect data from. So you want a smooth surface, like you want to understand the surface and how it is. So yeah, data needed. You have your georeference point, that is, it must have coordinate. All your data must have coordinate. Numeric continuous measurement, soil, pollution, rainfall. Then you have proper spatial distribution. That's very important. Your point must be well. That's why I said is either random or stratified sampling must be done, because you cannot just collect. Let's say you want to do rainfall prediction for Nigeria. You now use only the sensor in Southwest. You will not really get a good result. So you have to use all the sensors across Nigeria. So the result of geostatistical analysis involve raster prediction map or salinity map, like the error map, and then you can see your variogram and all those stuff. Then for the other parts, you can do crime analysis, head case, and etc. So yeah. So thank you very much. We will now be entering the demo session. I don't know if I should take any question before I go into the demo session. All right, let me just check the chat if there's any question in the chat before I go to the demo session. All right, I can't see any question here. So, all right, I think we have two hands raised. Is it a mistake?
No, I don't think it is.
Yes, I can hear you.
Okay, thank you very much, Samuel. My name is Oyindika Chigotra at Texas State. It's really interesting. Mine is not a question, but I just want to contribute that what you shared today is really powerful. It's one of the most important aspects of spatial data. And I just want to add, in the application, it's also used for bivariate mapping. And that bivariate mapping is one of the challenges why in a country like Nigeria, you will see the budget trillions of naira every year in the budget, but it's not implemented because we don't apply criteria. For example, how do you politicians will just locate police station because they feel they are from this local government, so the police station should be in that particular local government. There is no bivariance. So bivariance helps you compare different variables, just like you stated before. So it gives you the ability to do accessibility, ability network. People that are coming to your bank, what kind of transportation do they use to come? They drive or do they walk? So locating those factors have to be accounted for when locating. And all this is done using what? Spatial statistics and geostatistics. So thank you very much, Samuel. And we hope that some of these things we mentioned, we'll have more practical sessions on them. Thank you.
All right, thank you very much, Mr. Joshua. So thank you. You can now, okay, let me lower the hand. So Mohammed Tairu Mohammed, please, you just have like 30 seconds.
Thank you for this nice presentation. I'm a statistician and currently carrying my research in spatial Statistics at the Federal University of Technology, Akure. I'm so delighted with this your presentations. In fact, I'm so happy today. And the need for collaboration, just like we explained last time, is very important. My question is this: from the geostatistical analysis and that of the area, that's what the disease mapping you explained, is there any way we can merge that of the area data and the geostatistical data to analyze? Can we merge those two things together? That is the geocoordinate and the area, that is the points or the polygon ones together. Is there any possibility like that?
Okay. Number one, when you talk about geostatistics, you are talking about continuous variable. So when we are talking about disease mapping, the data are not continuous because they are mostly categorical data or just discrete data. So it is better you use your spatial statistics tool to actually solve that. And if you have points, you can actually do spatial join by joining your point to your polygon to actually get the count of occurrences. And after that, you can now use your polygon to generate or do any analysis you want to do under spatial statistics. You can also still use your point. For example, let's say you have point of all crime in Nigeria. You can actually do spatial join to join the count of all those points to the polygon, to let's say the LGA polygon, to know how many crime occur per LGA. Now, you might now take those LGA boundary to run something like hotspot analysis to see, okay, do we have more high hotspot of crime in Lagos LGA, or do we have it more in Abuja LGA? So you can combine those data, you can combine your point with your polygons to solve it. But when you're talking about geostatistics, we are talking about continuous variable, like continuous number, like rainfall, number that are in decimal places that are very continuous and has to do more with surfaces. So thank you. All right, so
Thank you very much.
all right. I will take the last question from Mr. Adamu Baba Mohammed before we enter the practical session.
Yes, sir. Thank you very much, sir, for the opportunity. I'm also with Yobe State University here in Damatru, Northern Nigeria here. I'm glad for joining this family today because I am neither a statistician nor a GIS specialist, but I have keen interest in statistics, and I'm glad to be here. Sir, I will be glad if the slide will be shared, though they said they will share the slide with us. That will help us to learn. Secondly, for someone who is neither a statistician nor a GIS specialist, I will be glad while running the practical session, maybe to come down to the level of learners like myself, who will take, understand it more, maybe more appropriately, for example, than people like you who are already professors in that. So thank you very much, sir.
All right, thank you very much, sir. Due to our time, I will try my best because a lot of stuff I want to run here today is just opening people's eye to it. So maybe we can have a full series on it where we dive into those two one by one. But what we are majorly doing here today is just to open our eye to the possibility of GIS and statistics. So while I'm explaining, I'm going to try my best to actually slow down and not be too fast. So that's all I can promise you, sir. Thank you very much. Okay, I think just let me take this last one. I'm checking time. Okay, I want to take this last one. Abdul Fatai Bello. Yes, please go on.
All right, good evening. I don't know, maybe you can hear me.
Yes, we can.
Good evening, everyone. Thanks for this beautiful opportunity. I'm very glad to be here. What I want to say is that you emphasize that geostatistics is dwell more on continuous analysis or something. Like
Yes,
it dwell more on continuous data, while spatial statistics are dwell more on points, data, stuff like that. But does it mean Yes, but does it mean spatial statistics cannot perform continuous data excellently? Because I
Okay.
know we normally use spatial statistics for IDW, kriging, and stuff like
No,
that,
no, no,
which
no,
are
no,
still
no, no. Spatial statistics is not. I've already explained that. IDW is geostatistics. Kriging is geostatistics. It's already in the slide. I already explained that. So spatial statistics is not that. Spatial statistics is all sport, moral eye, affiliate local, and etc. Yeah.
okay. No
Yes.
problem. You can continue on the practical aspects so as not to waste
All right.
time.
All right. Thank you very much. Thank you. All right. Let's go to the practical section. Ooh. All right. Um. Okay. Can everyone see my screen? I'm just sharing my ArcGIS full screen.
Yes, I can see it very clear. Very,
All
very
right,
clear.
thank you very much. Thank you very much. So, for the sake of today's lecture, I've actually pulled off some data. Some of them you just accept it the way they are, but let me send what did they used to call it? Oh, sorry, I've forgotten that English. But a disclaimer. This is for academic purpose. So yeah, some of the data are real data generated by different organizations, but this is for academic purpose. Don't go and cite my, don't go and cite me anywhere that I use the data and I said this is what is going on in Nigeria. But yeah, thank you. So we are going to start with geostatistics. And on my screen here, I already put this data in my ArcGIS Pro. Like I said, we don't have much time. If possible, I want to be done with geostatistics in the next 20 minutes and enter spatial statistics for another 20 minutes so that we can have another 20 minutes to answer questions. So geostatistics has to do with continuous variable continuous variable. And when you're talking about continuous variable, you're talking about something like soil mapping, you're talking about something like rainfall, air pollution, and etc. And with me here today is I have this data called Is That Soil. Anybody that knows the Is That Soil? Is That Soil is actually a company in Africa. Sorry, I might be switching within browser. Is That Soil? Just to give you an overview so that you don't get. So you can see is That Soil. They actually did some soil sampling around Africa, and then they now build different soil indicator like chemical property of soil using all this data. So if that now make this data sampling that they collected around the world, they make it available for us. So you can see is that soil. When time I want to do some remote sensing analysis, I used to download their data. They are also in Google Earth Engine catalog for those that use Google Earth Engine. So yeah, that's something about it. So these are the sampling that is that actually collected across Africa. Sorry, I'm not showing my base map because I don't want to slow things down. I don't want to slow things down. So as you can see, they collected 49,225 points, although some of them are duplicates. And then as you can see, they have the longitude and latitude. You have the date that they collected this. And then you can see these are the lower and the upper horizon of the soil that they collected data from. And you can see the variable they collected. This one is calcium. This one is carbon. This one is carbon total, carbon extract, copper. This one is for electrical conductivity, iron extract. So sometimes what these people used to do is they used to have collaboration with different universities so that when they collect their soil sample, they give it to them. Or sometimes they sponsor some research and this research collect all the soil sample and then they gather everything together. So out of this one, I click for Nigeria, but as you can see, this is Nigeria. They didn't really go all over Nigeria, but this is what they used to model their soil. So, but as you can see, they go to Niger. You can see that there are a lot of points collected in Niger. So because of that, I clicked my location to Niger State. So this is the Niger soil. So they've collected point for soil in Niger. Let me pick one thing we can predict. So let's say we want to predict carbon organic for the whole of Niger State. Like like I said, in geostatistics, it helps you to predict for sampling places. You see now that they went to these places to collect sample, but did not go to this place, did not go to this place, did not go to this place, did not go to this place. So how do we predict for all these places? That is what geostatistics is all about. So ArcGIS has already blessed us with a tool called Geostatistical Wizard. When you go to analysis and you come to Geostatistical Wizard here, you can click on it. When you click on it, you will see now that you have different geostatistical model. You have your empirical kriging, you have your EBK, you have your kriging, you even have the one for 3D, you have kernel interpolation. We have a lot of these. We don't used to have a lot like this. You have some deterministic model that you can use for your research. But for the sake of this tutorial hands-on, we will not be going through everything, but we'll be going through some of these models here. So let's start with the empirical Bayesian kriging. If you look at the explanation here, it says empirical Bayesian kriging, EBK, is a kriging-based interpolation method that account for uncertainty in semi-variogram estimation by simulating for many semi-variogram for the input data. So it accounts for location that data were not collected using a semi-variogram. When you talk about semi-variogram, you can actually do a research on that. It's actually a probabilistic statistical model. Those in statistics can actually do more research on that. I am not here to actually explain model, so I'll be fast as much as possible. But the major thing it's doing is to actually help you to predict for where samples were not collected. So I've already input the Niger State data. You see, I can select it here. Then I select the feed. I want to predict carbon organic. I click next. So now it's telling me that this carbon organic, that some points exist in the same location, which means they are duplicate point here. They are duplicate point here. And they did not lie, because when you look at my table here, this data here now is collected from 0 to 20 centimeter horizon, which means the first layer of soil that was dug to 20 meters. That was what they collected and recorded. So, but when you go to this upper part, from that 20 to 50, they dug another soil again, which is another layer. They collected another point. So those two are now overlaying each other. So what should I do? I want to use the mean. Like whenever you see 2 points intersect each other, since we know it's a single point, but they just try to like get the sample from different layer, just calculate the average. So you see, it's already giving us a semi-variogram. You can see that each point have their own semi-variogram line that is trying to use to estimate what it should be. You can see you have a nugget here. This nugget is showing the density and the value, just to show the distribution of your data. You can see the slope of your data. You can see the curve, the power of your data. So it's using this semi-variogram to actually estimate each line you are seeing here, represent each point. You will see that there are some red lines here. These red lines, they have their different meanings. Sorry, I want to show the legend. I think it should be here. Okay, sorry. You see, it's trying to estimate now for this location. So you can actually edit all this stuff. You see, the output surface type is prediction. So you can have a probability. So that probability surface is going to give you the probability of that place being predicted. You can have a prediction standard error. Like you want to see the error of your prediction, you can see the surface here. In IDW, you don't do all this. You don't have the power to tune all these things because it is direct. So we want to see the probability. No, let's see the prediction. You can increase the number of simulation. It's actually simulating your data if you increase it to 1,000. You see, say specify the number of variogram will be estimated. That's too much. It might take our time. So it's using how many smooth circular. You see? When it's using smooth circular, it's not giving you a standard result, then you change. All these things, like I used to tell people, they are experimentation. The only thing you might need to do is to read about all these stuffs. I did not want us to take us through the app because if you, let's just do that. If you go to, sorry, let's do EBK app in ArcGIS Pro. When you come here, you can see it actually explain what is happening here to you. The output raster displays the result of interpolation. It explains everything that is going on here with you. 4 sector shift. So you might need to come to the app to actually understand if you want to learn more about the EPK regression prediction, you can actually click here. When you click here, it gives you the understanding of how each and everything works, like the error, the statistics behind everything. But as a scientist, this process is called experimentation. You are meant to actually play around with it, till you have a very better result. As you can see, we are still not getting a very better result, but we can decide to go with the standard circular. So the next thing we do is click on next. When you click on next, you can see now, here is your predicted value. You can see something like your regression line, and then you can see your point here. You can see your point here. You can see your regression, this thing here, your regression equation here. So this is your reference line from 0 to here. You don't need this. This is your predicted regression line. So you can now see now, if you look at this now, this is the best fit line. And then these are your points. And you can see, like, we can call these outliers. You can see how they are far off from your best fit line. And then you can click on error to see the error. It's plotting your error against your regression line for you to see. Here you can see your standardized error. This standardized error is like, okay, they've tried to normalize your data to see even if it's standardized, we used to be having a better and correct result. Your normal QQ is actually another statistical plot that is used to actually use to evaluate your model based on the slope. But when you look at all these things, you look at the probability, continuous probability score, you look at the measured probability, you can even see that this thing is skewed. It's not normal standard error. You can see how our error is fluctuating. So when you come here, it shows you the total count of the point, 716. This is one of the most important things we used to see. RMSE. Your RMSE, the closer to 0 it is, the better. You see, you have 4.4, you have your mean standard, you have your 0.3, you look at your average standard error, you have 4.4, and you look at all this. Well, this can look better for some people, but as statistics, as a data scientist or a geospatial data scientist, you have to still go back. Like I said, not like you are playing around with all these things. You can increase the number of neighborhood to 30. Then you try to like nest to see the result. Okay, when we increase the number of neighborhood to 20, is only having a minimal effect on our RMSE. And what about our prediction line and all those things? You go back again. If you are a data scientist, you understand what we are trying to do here. You can also increase this radius, minimum this thing, you can set it to 5. You can reduce the subset to 50 and just try to nest it. Oh my God, the error has increased back. So maybe the success should be increased. So it's just like in machine learning, where you try different model to see the best one that will give you the best result. So after you've played around with all these things and you check all this your score, our RMSE, sorry, I did not put it in my chart. For those who know the root mean square error, it actually calculates it actually calculates the error from your predicted to your linear fit, and then it summarize everything together and calculate the square so that it can give you a single value that represents the error. So different people have different parameter that they use to measure their error. But when you are using regression, RMFE is a very, 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 very useful parameter. And it is always better when it's closer to zero. When it is closer to zero, because because for you to calculate your RMSE, you've calculated the SS, which is the sum of square error, by actually calculating the differences between your line fit to your point and after all that. So just like I said, in your IDW, you don't do all this. You don't have all this stuff. You don't have all this chart to support whatever you do. So imagine if you want to do like rainfall interpolation for Nigeria, you need all these variables. You need all this core to be presented in your table for us to be able to accept your result. Just like I tell you, you can see now that in each point, we have the validation contact, the continuous ranking, we have the standardized error. You see the predicted. This is the measured. This is the predicted value for each measured area. This is the predicted for all these places. And then you see the error for all these locations. So we can now click on finish. So when we click on finish, I want to hide this, sorry. So when you click on finish, it gives you a report like this. You see prediction, and then you click OK. So you have a result here that actually give you an interpolated result. You can see now for all these locations. Sorry, let me uncheck this boundary. Okay. For all these locations where there is no data, you can see this is the predicted. You can see this is the predicted. It's predicting for here. It's predicting for all these different locations. When you go to the feed, you didn't collect data for all these places. You did not collect data for all these places, but it's predicting now with statistics. So you can still right click here and go to cross validation. When you click on cross validation, you can still see your result. You can still see your report. You can still see your table. All these things are what you use to actually show us if the modeling you've done is right or wrong. So you can still close this. You can still right click here. You can still export the layer to a raster. So if you want to export it to a raster now, you can now click here. Here it's not a raster here. It's still a predicted surface. Sorry. This is still like a predicted surface. So here you can now name it. You can now put the number of cell you want, and then you can now output it as a raster. There are a lot of stuff you can still do here. You can export it as a contour, and then you can still open it back. This is it. You can still open it back. You see? You can still open it back. You can still see, you can still go back and change all these parameters. You can still go back and change all these parameters and etc. etc. So yeah, that's all about geostatistics. And just like I said, you can see a lot of other too. I love kriging. Why? One thing you should notice is that this empirical Bayesian kriging here does not allow you to add a dependent variable. But when you come here, sorry, does not allow you to add your independent variable, which is your X. It does not allow you. You can only put this. You cannot put other layer that actually influence it, which means I can only use carbon organic to predict carbon organic. What about if there are other factors that are actually influencing carbon organic? How do I bring them into this? That is why you have your EBK prediction here. It supports that, whereby you can have rasters. Let's say you have another raster of DEM, you have another raster of rainfall, you can actually add them here. Or you have a subset polygon. This one now, you have a subset polygon. It will predict inside that your polygon, you see. It will also ask you what you want to use to measure your error. So let's say we pick this. We don't have a raster, this thing. Let me say we want to use pH to measure our error, but we don't have a raster. This one, if you have rainfall, you have DEM, you can select it. And for this one, also, this one, if your data have other things that you can use to predict, that's one of the things I love about this. You can also add them because there are some things that influence something. For example, let's say for carbon organic now, some of the things that actually influences is rainfall, is NDVI, is is pH and all those things. If you have those stuff in raster and you have them downloaded, you can actually upload them here. You see kernel interpolation here too. You can actually put a weighted feed. What a weighted feed does is that it wants to predict for organic carbon, but everywhere it sees pH, it looks at the weight of that pH in that location and then say, okay, due to the weight that this pH have, the organic carbon in this place should not be more than this. So like I said, this is the disclaimer. My data here is just a practical data. When it comes to real life, you have to do your correlation analysis. You have to know the data that are correlated to one another. So you don't just go and do it the way I'm doing it right now. You need to have all your data set to know, okay, what is the relationship between this and this? That's why I said maybe when we have like a full day, because this might probably take 2 hours if I have to break down everything explicitly. But the main goal of today's course is to show you the possibility of all this stuff. So let's say I want to do this kriging. I want to use another data. So let me use rainfall data. This first raster value is actually a rainfall data extracted by errors. Then let me select this rainfall. This second raster value is actually a DEM selected. I've actually renamed all this raster value here, but I didn't know why they renamed there. So let's click on next. So what this is going to do, that's one of the things I love about kriging. See, kriging will show you, do you want a simple kriging? Do you want an ordinary kriging? Do you want this different kriging? There are a lot of different types of kriging. So it will now tell you what transformation do you want. This one will do standardization on your data. You next it. You see, it has standardized my data. Can you see? You see, my data is skewed. As you can see, my data is skewed. So how do I make my data better? I can try to like transform it, doing something like linear approximation or anything. This is my second data set too. You can see it is skewed. So this one allows you to do a lot of transformation. This is Gaussian kernel. Okay. It's still not okay. The data is not looking too good. So like I told you, it's just a data extracted from the satellite data. It's not really a real life data. So it showed you your plot not appropriate for this linear estimation. So let me see. Okay, Gaussian kernel is looking good here. Okay, so let's go with this. Can you see? So this is using a covariance map. This is you see the model. It's trying to plot for each location. So I can actually use a semi-variogram for one and use anything I want. Let me leave them as semi-variogram. You can actually select the model you want, the error. There are a lot of models here. You can select them that you want. You can select your number of lag. You can select a lot of stuff, and then you click next. You see now it's giving you a prediction surface, just like the other one, but different model. You see now this one is giving us, this is for the rainfall I am trying to predict. This is not for the carbon organic copy. If you remember, when I was trying to predict rainfall, I have a DEM, an elevation data, because I believe that is a correlation between elevation and rainfall. you can see the result of what it's trying to predict here. So let's see. Let's see my rainfall data. This is my rainfall data here. So you see now, it's trying to predict rainfall for all this interval. So let's see this point. What's the rainfall value on this point? This point shows 77 millimeter. Elevation is 7. But when you click here, you see it's predicting 44. That's the rainfall. I think 74 millimeter, because the rainfall unit is in millimeter. As you can see, it's predicting. So this is better than your IDW, because IDW will not allow you to actually edit your model like this. You can still open back and go to your model and apply different transformation to see if that will make your model better. You can actually disable this. You can increase your number of lag to 15, and you can still continue. Oh, this is not giving us a better result. This is not giving us a better result based on those our metrics. You can click on your cross validation. You can see your metric. Our RMFE is very close to 0 before, even our average standard error. But when I change the transformation, you can see that the error has become no better. So after you've done all this analysis, you can then export, just like I've showed us here. You can export your layer to a raster. So that's all about geostatistics for now. Maybe in the future, we are going to take it on and break down all these two one by one. So that is why we tell you that if you want to produce something like PM2, PM 2.5, or you want to produce something like diseases and everything, and you have different layer, independent variable, you can't do all those things with IDW that can help you to predict a better result. You can actually add those layers. You can do transformation, and you can have a better predictive results. Okay, so thank you on this. Part 2. Okay, I'll answer every question after this second one. Spatial statistics is actually one of my favorite parts when it comes to GIS, and I will tell us why. Because it actually helps us to make sense of our data better. It actually makes us to make our data better. And thank God for ArcGIS toolbox. In your ArcGIS toolbox, you have your spatial statistics tool. This is it. Inside this your spatial statistics tool, you have one that helps you to analyze pattern. You have one that helps you to assess sensitivity. We have one that helps you to map cluster. And we have the one that helps you to measure geographical distribution, and the one that helps you to model relationship. And we have a lot of them. But we'll be looking at some of them today. One of them that we'll be looking at is average nearest neighbor. So what it helps you to do, it helps you to calculate a nearest neighbor index based on average distances. When you open this tool, this is not going to take time. You see, it shows you reports. It does not give you an output data. When you click here, it tells you that it gives you a report to tell you that is your point dispersed or cluster. That's just all it tells you. So I have this data. This is crime data for New York in January 2025. Different type of crime. If you open it, you can see the boroughs where it happens. You can see the date. You can see the type of crime. Is it felony? Does it happen inside the house? You can see the offense description. Is it rape? Is it harassment? Is it assault? You can see a lot of this. So we have this point of 45,000 points. We want to know if this point is cluster or disperse. I know you can say, looking at this, it is cluster or disperse. I know you can say that looking at it, but you need to be able to support these things scientifically. And that's where the average nearest neighbor actually come into play. So I'm going to input this here. And you see, you check generate reports. and then you run it. You wait for it. It will generate your report. You click on view details. Once you click on view details, it gives you a z-score value and a p-value. You can see your p-value is less than 0.005. So what this place is already giving you based on this p-value is that this is clustered. But when you open this result, you see clustered. It's showing you that it is clustered. And you can see it, the significant region. You can see it, the z-score, the nearest neighborhood ratio. You can see the p-value is less than 0.000. Everybody that know what p-value actually mean when it comes to model significance, you will understand what I'm saying. So it's telling you that given the score, the z-score of minus 4.4 there is a less than 1% chances that this cluster wood pattern could be a result of random chance. So what this tool is actually testing against is randomness of your data. And you can see this report. This report has actually aided you instead of you using your mouth to say, oh, it is cluster, it is random, it is dispersed. Just running this tool has already helped you with that. We also have some of the two. I'm looking for one in particular, measuring the geographical distribution. I love this too. Why? It helps us to know directional trend. For example, let's say I want to know the trend of this disease, of this crime activities. Is it tweeting to the left? Is it tweeting to the right or to the right? I mean, how plenty are they directional to understand their trend? You can actually open your directional tool and then give it this. One thing about directional tool is that it takes in the count. So because we've not aggregated this data, we do not know the count of each crime. So that might be difficult for us to run this through. But when you want to know things like, you want to know things like central fissure. Like, this point is plenty. You cannot know the center point where we are having highest number of crime. This can help you to decide that. As you can see in this picture, we have high distribution, but this place is where we have a lot of crime. And then this is the center of the crime. So this is one of the two things that these two actually help you to solve from. So when you put this there, it will generate a point. We might not put all this weight feed depending on what you are running for. Those weight feed, they actually works when you have a table where you have the reason why I cannot do that trend the other time is that I don't have a column. I have a count of crime. If I have a column for that, the directional trend would have been very, very easy to understand the direction of the crime. I love that too very much. I love it very much. And then you have the mean center, the media center. These two are very important because as a geospatial statistician, we don't expect you to just look at map and tell us it is southwest, it is northwest, it is east-west. No, you can run a directional trend analysis to understand the direction of those two. Another thing you can also run is, you can see, this is telling me that there is more crime. This is more of a center point for the crime. A normal person will put the point here because when you look at the distribution, the point should be here. But this is telling you that this is the center of the crime because when you look the crime here, and when you look the crime here, this is the center of the crime. You looking at this, you cannot answer this by yourself until you run analysis like this. Some of the things we want to also look at, I want to be very fast, is you can run this. You can run optimize hotspot. But the thing with optimized hotspot is that you need a feed to run it. So I'll be using a feed to run some of the other two now because you need to calculate a feed. I just have to show you this using this data because if I want to run a better analysis with this data, just like the other person was talking about collecting crime data, I will need to join all this data to their polygon and know the count of different type of crime. So that alone might take me time because I need to filter and group by all the crime that occur and then do the count by the group by, then now sum it, then now join it back to the polygon. But currently, I won't be able to do that due to our time. So it's just to show us the possibility of what we can do with all these two. So I'll be leaving the crime data, then I'll be picking another data here. I have this data here. Let me just use it. This data is called the US health ranking data. You'll be asking me why I'm using US data in your mind. It's because Nigeria did not have the level of data to run some of this analysis. That's the actual truth. That's the actual truth. So one thing we want to run here is we want to model spatial relationship. See, we cannot exhaust these two. We cannot exhaust them. You see these tools under geostatistics. Every version of ArcGIS that come out, there's always a two. So let's run OLS. OLS is ordinary least square. It's actually used to understand relationship. If you can see, it performs to generate prediction or to model dependent variable. So it's a regression model that does prediction, but as GIS people, we are more interested in the relationship it sees rather than the prediction it observes. That's something. So it used to generate a report. So I'm going to use this American health data to run something. So I'm going to input this health ranking. It needs a unique ID. If you see, this counting FIP is actually unique. County FIP. Coming. I need a unique ID for this. I don't know why it's not taking all the other unique data. Sorry, I'm coming. No, this is not unique. Why is it not sorry? I'm surprised it's not showing those data. So let's try to create a new feed to give it a unique number. Feed calculator. ID. Looking at there's this sequential number or something. So I think I've given it a unique number. Let me look for that ID that I created. Sorry, ID. Okay. I can find the ID. Professor. Sorry, I've created a feed call ID and I can't find it. This is strange. All right, let me just pick any of the random feed and hope any of them is actually unique. Okay. I don't think it's unique, but I'm going to try it. So let's say we want to see the relationship between smoking adults. Let's see. Adult smoking. Let's say adult obesity and I don't even know what I want to look like. Let's see life expectancy. Let's see number of drug poisoning. Let's see that. Okay, then we have a report. Let's call it OLS report. Let's run it. I don't think this is unique. These two require at least 5 feature to complete results. Okay, 5 feature. I think let's see number of adults. Let's see that. Only an error. I think that unique will still give us error. Okay. The input feature does not apply to contain projected data. Problem reading 3 or 3. Feature with bad record only include too few record for this analysis. Sorry. I mean, let me see if I didn't select anything. Okay. I selected more than 5. I have to use another data if this data is given this issue. I never expected it. Okay, I would love to use another data. I have another data here. So this other data I actually have is not on American Health Ranking. I'm even surprised it's not seeing. This data I have here is actually on HIV/AIDS and some other sexually transmitted disease and the rate at which they happen at different county in US. I just thought that we should just use the US Health ranking data because it has a lot of attributes. But I'm surprised it's not allowing us to run our analysis. So, yeah. Okay. So let's go back. For the OLS, is used to understand relationship, just like I said. So I'll be using another data entirely, which is the USA with HIV/AIDS. So look at this data. It's talking about HIV cases and how it affects different people, not only HIV and their mix of translation, and it's talking about even other cases like syphilis, percentage of people living with HIV, and the medium household incomes. So let's see the medium household income. If there's a relationship between medium household income, I think something is wrong with this data because this is actually working. Medium household income and let me see, HIV, male rates. Let's see male rates, heterosexual female. Let's see household income, median household income. People, percentage of people living in poverty, if it influencing HIV, percentage of people less that not graduated with high school, if it influences HIV. Let's see if percentage people living unemployed, people uninsured. Okay, let's see OLS report. Let's run it. So as you can see, it gives us a standard deviation error, which is giving us the prediction error on how what we just run now is performing. So as you can see here, we have less than 2.5 standard deviation error, and here we have greater than, you can say, oh, in where we have less than, we can say our model is performing best. But in all this area, when you compare the predicted and what is actually happened, you can see the estimated number of people with HIV here should be 427. I think we're actually predicting male rate. And you can see that the male rate there is actually 2. So it's not even correct because that data is showing negative. And here you can see that the male rate is showing, the estimated here is showing 410, while what is actually here is showing 116, which means what we used to estimate is not even giving us a better result. But let's go and view our OLS report. So OLS will actually give you a lot of details. You see, it's also telling us that like 30 features, so 22 record actually have issue. So that might also affect the accuracy of our result. You can see all the statistical property, like your R square. You can see we have a very low R square. So that cannot be acceptable. And then it also gives you a report. That's one of the things it does. It gives you a report. So you can open your report. I'm opening my report. So the report is actually going to show you chart. You can see this is male rate versus heterosexual living. You can see that there's no even real correlation. You can see, and our data set is showing outlier. Is not really modeling our data well. You can see how the predicted and how see the line, the prediction line. You can see how a lot of our data, you can even see this astral line. This one self alone can make our model not to perform the way it's meant to perform. So you can see all this stuff. Then when you go to these places, you can actually see their statistics. You can see their probability. You can see that this one is out of it. Then you can look at their VIF. There's actually, you can, when you go here, you see their meaning. Large VIF value greater than 725 indicate redundancy. So when you go here, you can feel okay, your data is okay in terms of VIF. Then when you go to coefficients, represent the strength and type of relationship. He said probability and robust probability indicate a coefficient is statistically significant, that is greater than 0.1. So it's telling us that 1, 2, 3, 4, 5 looks good. So median income, percentage, all these things does not determine if a guy will have HIV or not. That shows they has nothing with the HIV. So you can rule all this out. So when you go back to do your OLS modeling again, that shows all those other properties. You have to remove them. So that's why I said you have to do all this analysis. Apart from OLS, we have a lot of them. We have this one, exploratory regression. This one is just like your normal regression. It will give you the R square, the statistical value, the RMSE. It's going to give you all those results. That's how this one works. And as you can see, this is how this one works. And when we go to something like hotspot analysis. Sorry, I really want to be fast. When you go to hotspot analysis, let's say we want to know the hotspot of that particular. I want to see if this data will work for hotspots. Let's see. We want to know the hotspot of adult smoking in USA, percentage of adult smoking. We want to know the hotspot. So let's run it. I want to know if this data is okay or not with this. All right, you can see the result. So this place where you have red is giving you an hotspot with 99% interval. So there is high number of adults smoking in all these states. High number of adults smoking in all these states. So sometimes you have to do a little Google to confirm this stuff. Sorry. You have to do a little Googling to confirm this stuff. So let's just do something to confirm, a little research. State with high adult smoking in USA. Let's see. West Virginia, Arkansas, Mississippi. Let's see these states. Oh, it's not going to show me the state, so I'm coming. Let me put this on it. Let me actually remove this and see the state. Which state is this? Arkansas. That's Arkansas. So you can see that the data is already revealing something to us if you look at that. And then now you can see all this hotspot. These places means that the number of people, adults that smoke here are not that much, according to the 99% interval. What this place significant is telling us is that this place is not random, though. You cannot say 99% all sports. You cannot say 99% cold sport, because this place might have high number of people smoking. This place low number. This place low number. This place low number. So there's no reason why you should call this place an all sport. So for example, now even within all these all sports, they are still low sport. But because they are within a place that has all sport, that's why they are categorized as all sport. So how do you know that there are some places that has cold sport within all sport? That's where you need something like cluster outlier like this and Selenium. So you can actually put the same data there. Some of this stuff we are supposed to just come one day and pick it one time and just work on them. So I'm giving it the same data now. I'm just running it. I'm not editing anything. I'm using all the default variables. So this one now will show us the code spots within our spots. Okay. Can you see now? This place is an hotspot, right? But these places, they are cold spots. But the reason why they are categorized as hotspot by the hotspot too is because they are surrounded by hotspot. So because they are surrounded by hotspot, you will think they are hotspot. Yes, this location entirely is hotspot, but within that hotspot, they are cold spot. These places are cold spot, but within that cold spot, they are also hotspot. But this, you see, the way this thing works is that it look at their boundary. You see now, this place is sharing boundary with cold spot, and it's only sharing boundary with like one hotspot. It will tell you that that place is cold spot. But this place, that means in your tool, when you run your hotspot analysis first, you need to run this other one for you to know us. You can see that it's saying low high outlier. It means low percentage of smoking within high area with high percentage of smoking. That's what this low high mean. The high mean you are high low mean this place is a low cluster, but this cluster, this small place, they are very high. So we have a lot of tools that we cannot even check out because time will not even permit us. As you can see, the spatial statistics have a lot of tools you can use to perform all this analysis and more than this. So without taking much of our time, I will honestly, sorry. Without taking much of our time, I would like to stop tonight's class here because there's still a lot to cover. But like we said, this is a starter pack for you to know what is possible. Maybe when we meet next time, we will just pick maybe only 3 or 4 tools. And then we will look at the possibility. We will explain them in details. Maybe it will be only kriging we'll talk about that day. We will talk about kriging, the advantage, the disadvantage, and everything within kriging and what you can do with kriging. And we have more example of kriging. But for today, I believe we've been able, or I've been able to, to introduce us to some things and to tell us some possibility within GIS. So thank you very much. We now start taking question. Thank you.
Thank you very much, Samuel, for that powerful session. Actually, I enjoyed it, and I know that a lot of us here actually had a lot of things to take home from this training. So I know that we've spent almost 2 hours on this call, but it feels like we just spent 30 minutes, and we would like to take a few questions. Sam, can you check the chat box? There are some questions for you there. So if you have questions, our time is almost is fast spent. So if you have questions, you can just drop them in the chat box or raise your hand. We'll entertain just 2 questions if your question is not on the chat.
Okay, I think I can answer some very quick. Please, can you talk about your graphical weighted regression model? Yeah, I didn't really show GWR because GWR is just an advanced OLS with, with much better strength. It does prediction better than OLS, and it helps you to understand the relationship. So yes, like I said, all these things, we have to compare and contrast them. There are a lot of things that do similar things, but strength is what you need to look at. Like, for example, you can see hotspot. You can also see another tool that show you cold spot within hotspot. Do you see now that they do almost similar thing, but with different strength? So that's just the way all these tools are. And what you just did be demonstrated in GIS. That's one issue I have with GIS. I'm also a fan of open source, but if you want to do some of the thing I'm doing, you have to go and learn Python using PySar, or you download Geoda. Geoda is actually a geospatial tool, open source tool for statistics. You are going to be using Geoda because Geoda even have things that ArcGIS Pro did not have, to just say the truth. But ArcGIS Pro is topping their game. Like, I don't even know some of these tools are there until I open this my 3.5 because I've not even been inside this toolbox in a while. They are adding new things every time. So you can't use QGIS, but they are open source geospatial statistics tool like Geoda. Yeah, using p-value. Yes, Mr. Joshua already explained that p-value. I already talked about hypothesis. Like, there's a general null hypothesis in GIS. Everything is random. That's general null hypothesis. So you reject that by saying it is not random, it is dispersed, it is cluster, it is this. So that's where your p-value has to come in. And if yeah, R is a very good research tool, very good research tool. And if you know how to write Python, check out PyStar. It's a very good tool. Like, PyStar is very good, very good. And a lot of all this thing in ArcGIS is built on PyStar. Yeah. Are there going to be courses with certification on GIS? I cannot say that, but the team will answer that. I think someone should just respond to that question. So yes, I think I've just justice on that part. And I don't know if anybody have any question. I think we are done with the chat. Yeah.
Okay, I don't think we have questions for now. Maybe
All right.
if you have questions, you could reach us on our LinkedIn page. Okay. The link to our LinkedIn page is on the chat, so you could reach us there, and then we would attend to your questions on this our training for today. Or if you have any other question relating to
Okay, I think we have a
spatial and
question.
data science.
I think we have a question from Shahib Inua.
Yeah. Good evening.
Yeah, good evening.
Yeah, I can see that the lecture has been recorded. I am asking if there is a way we can get the whole record of the lecture, because we've been going to prayers, and I know we have missed some part of the lecture. So this is it.
Yes. The recording will be sent to our email since we register for these courses. And also, when it is being uploaded, it will be on our social media LinkedIn page so that people can actually watch.
Okay, and then the earlier slides, is that possible we get them?
Yeah, everything will be sent across. Everything will be sent across.
All right. Thank you so much. Thank you.
All right.
Okay.
So, in the absence of no question, I want to appreciate everyone coming here because I understand. I know that the number was at a point 60 something or so, even though some people have left, and I want to appreciate those that come and those people that wait to the end of this program. One of the encouragement we need as a group, as an organization, is when we have people keep showing up. We also will continue to do our best. So, this is just the beginning. It's just an introduction. There are still a lot of things to explore. Just like I said, our next class can just be on kriging, and then we just use kriging and then we bring different type of data, PM 2.5 and everything, and then we do modeling, and then we create something very, very special. And from all these things, if you can be creating your research topic from there and be working on a paper, because that's part of what we plan to do as a group. So I want to give shout out to the organizer and to the leader of the community and to everyone that has been part of us from the beginning to now. So once again, my name is Jeremy Adedoyin Samuel, a geospatial. I'm sometimes confused on what to call myself. Maybe I call myself a geospatial specialist and a lover of geostatistics. So thank you, everyone. Rikia, please take over.
Okay, thank you so much for the closing remark from you and powerful presentation, I must say, powerful training. And I'm sure everyone learns and have one or two to take home from this, like I said earlier. So subsequent trainings would be published on our social handles and be sent to our emails. So do well to register on our website if you've not. And also subscribe to our also you could get your membership certificates, like I mentioned earlier on this call, on this call, yes. So without further ado, we would like to call it a day and appreciate everyone for being part of our training session today. Thank you so much for spending your evening, your weekend with us. We appreciate your presence here and do have a blessed weekend. Thank you.
Thank you. And have a lovely evening.